In this video, we're going to continue our discussion of the Gibbs free energy in relation to equilibrium. So previously we discussed the free energy in relation to the equilibrium constant when at equilibrium. What if our mixture isn't there? What is our available Gibbs energy if we're still somewhere before equilibrium? Well, for this, the RT times the ln of Q over K. When our reaction is occurring, as we are approaching equilibrium, we'll have less and less available free energy. The reverse reaction will be occurring often enough to counter the forward reaction. There's very little net difference left to occur, and so very little work could be harnessed. But as Q and K are more different from each other, then there'll be a greater change available for the system. More molecules will still be able to go one direction than are coming back from the other, giving us a direction of reaction that will continue to flow for a while. So the amount of free energy still in our system is dependent on how close to the equilibrium our actual mixture presently is. So that free energy, we can break this apart, RT ln of Q minus the RT ln of K. In fact, it's from this equation that we were able to identify the one we've used previously, that the delta G at the standard state is equal to the negative RT ln of K, because at standard state conditions, your concentrations would all be 1. Whatever your reaction quotient is, 1 to any power is still 1 divided by other 1s, just comes out 1, and the ln of 1 is equal to 0. So at standard state conditions, this front part disappears, which is where we get our standard state free energy should be equal to the negative RT ln of K. But if we're not at that standard state, if we have different amounts of our chemicals still, so Q is anything other than 1, then I'm going to have some value subtracting another value. Well, the larger Q is compared to K, the bigger our front number is going to be. So when I then subtract it, I'm going to still have a positive value. If Q is greater than K, then delta G is positive. If our Q value is ever less than K, then our delta G is negative. And if Q is equal to K, we're at equilibrium. Delta G is equal to 0. Well, remember that this is an equilibrium reaction. When we say that the delta G is positive, that's for whatever reaction direction we wrote the chemical reaction for. So N2 gas plus 3H2 gas in equilibrium with 2 NH3 gas. In this case, we've determined which were products and which were reactants. But if we'd flipped this around and just done it the other way, well, we've swapped which is on top and bottom in the reaction quotient. If I have a mixture for the top here that says I have some ammonia, I have some N2, and I have some H2, all that's going to be equal to Q. For those same amounts, the next reaction would just flip what's on top and bottom. You'd get the inverse value, which would change when we do the subtraction whether what you calculated out was positive or negative. If delta G for the first reaction is positive, it's negative for the reverse reaction. Instead of looking at just a reaction that goes in one direction and looking at Gibbs free energy to decide whether it was spontaneous or non-spontaneous to occur at all, when we have equilibrium, we have two reactions. One of them is going to be spontaneous in our given mixture, and one of them is not. Depending on what our concentrations is, we'll determine which of these is spontaneous or non-spontaneous. So when you originally calculate out for our original reaction, N2 plus 3H2 goes to 2NH3, that the delta G is positive for some mixture. What that means is that it's negative for the other mixture. So when you're investigating the present concentrations of an equilibrium reaction, if your delta G is positive, it proceeds to the left, reactants. If your delta G is negative, then it proceeds to the right, products. Occasionally this is a little confusing. We say that delta G is positive, and most folks think, well, then it shouldn't be spontaneous. But that's the forward direction is positive. The reverse direction is negative. And so in our first situation here, we're not likely to go in the forward direction. That's disfavored. We are likely to go in the reverse direction. And so we tend to move to the left and make reactants. If your delta G in this calculation, however, is negative for the reaction you wrote, then it is favorable to proceed in the direction the reaction was written, which means you would go to products in that written reaction. You would move to the right. And as always, if they're equal, you're at equilibrium. Neither direction is favored, so your concentrations will no longer change. So let's solve the delta G of the system. If we have 0.5 molar HCl, 0.2 molar H2, and 0.7 molar Cl2. So this reaction that says two HCl's are in equilibrium with H2 and Cl2. At standard state, the K value for this equilibrium is 3.9 times 10 to the minus 34. We can tell right away from the K value, very little products, mostly reactants. So we don't expect this to go very far to the right, and if we check our values, well, we actually have a fair amount of stuff. So we can solve our Q for the moment. What is our Q? Well, let's give a reaction that's going to be our H2 to the first, our Cl2 to the first, our HCl to the second. 0.2, 0.7, 0.5 to the second. Our Q is 0.56, so about 33 orders of magnitude off. This is quite different. Well, let's plug it in and solve what our free energy is in this present mixture as it drives the reaction mostly towards products, it looks like. Well, the RT ln of Q minus the RT ln of K. What is propensity of our present mixture versus where it will be at equilibrium? 8.314, 298. Our K value here was the standard state 298 K value. ln of 0.56 minus 8.314. Guess include units, joules per mole Kelvin. 298 Kelvin. ln of 3.9 times 10 to the negative 34. Negative 1436.5 minus negative 190592. In both cases, these will be joules per mole. In which case, the free energy of this system is positive 189,155 joules per mole, or positive 189 kilojoules per mole. That is extremely positive for the reaction as written. This is not going to favor moving to products. The forward reaction is non-spontaneous. So this is equilibrium. The reverse reaction, therefore, is. The H2 and Cl2 will combine to make HCl quite readily. The reverse reaction is negative 189 kilojoules per mole. That is a great deal of free energy and is spontaneous. And so we would expect that this reaction would move to the left as written, that would move to make HCl's. So using this relation between the present reaction quotient and where it should be at equilibrium, we can actually determine the free energy available in this mixture of an equilibrium reaction.